In this short video, I'd like to demonstrate how to calculate using Excel these different error measures that we've introduced in Module 8. So let me kind of get to work on that. The first thing, we have to have a forecast. Now, the forecast came a couple of modules ago, so I didn't redo how to do the forecasting. One thing I do want you to notice, though, this historical data that we've collected, generally speaking, we're talking of forecasting future dates, okay? Well, and that's what we want to use it for. But in order to calculate the errors, I have to know what actually happened, A sub I, and I need to know a forecast. So thinking about it, we're creating these measures of how good our model is based on what it would have done in the past. Now, I don't want to get caught up in the philosophy of that, and don't let it bother you. It still though is saying implicitly that tomorrow things are going to be more or less like they were yesterday and the day before. So with that said, let me start off by calculating a deviation. Deviations are defined as the actual value taken by our variable minus the forecast value. So notice we're not going to be able to calculate a deviation for week number 1 simply because we don't have a forecast for week number 1. So here we go. Actual value minus forecast value. So what can I tell you from my numbers? Well, deviations, I'm interested in the sign that comes on my number. So what does it tell me if the sign is positive? Well, it tells me that I under forecast. So I'm a little low. So I can look down at all of my positive numbers and say, okay, there are many times when I under forecast in this particular problem. A negative sign says I have over forecast. And so you can see there's a few of those as well, that I have over forecast when using this model. So what do we do now? Now, the first measurement of error we had was the MAD, so that's the mean absolute deviation. So let me construct the absolute deviation. So in Excel, ABS is a short notation for absolute value. I'm going to take the absolute value of the deviation, and then if you recall, the mean absolute deviation, well, I've already taken the deviation, the D part of MAD. I've already taken the absolute value, the A part of MAD. Now all I need to do is take the mean. So I'm going to take the average of these absolute deviations. And there is my mean absolute deviation in this problem using a forecast tool of just a simple forecast. All right, the next tool in our kit was this cumulative sum of error. Now, this one we could have done earlier. All it is the sum of these deviations. Now, two things I'm looking for in this number. One of them is the sign. The sign being positive means that I am consistently under forecasting with this model in this problem. The magnitude of the number, which is always got to be relative, but the number 33, not particularly big, but in this model it might be. I don't have anything to compare it to. But the magnitude of the number tells me how bad my forecast is. Or another way of getting to how bad the forecast is to calculate the bias, which is the average. Sorry, it's just the average of these deviations. So positive, just like the cumulative sum of error was positive, because it's showing the exact same thing. The sign on the bias, the sign on the CSE being positive tells me that I am under forecasting, and the magnitude of the bias, 2.35, don't really have any meaning for that yet. We may not until we have another type of forecast, for example, some sort of moving average or some other type of forecast to compare and say, okay, well, this one has less bias using this model than it does using a different model. Now the mean sum of squared errors, there's really nothing left to calculate here. What I want is the sum of the squares of the deviations. I'm not quite done. I want to divide that by the count, the number of calculations minus 1. And that will give me the mean squared error. Okay. Now I was expecting it to be positive. Remember, I'm squaring everything and then I'm adding up a bunch of positive numbers. I expect that to remain positive. So the sign doesn't mean anything here. If it didn't come up positive, you did something wrong. The magnitude is what matters here. The mean squared error will act an awful lot like a variance does in a standard variance calculation, which what I mean by that is larger deviations like this 15 right here contributed a lot more to this mean squared deviation than the deviation anything smaller. Even this 7 added much less to the mean squared error. 49 is 7 squared. 15 is what, 225 squared, somewhere around there. So this is adding a lot more to the mean squared error than is this term, and especially even this term, whose square is just 9. So the mean squared error, what it does is it picks up on those bad large forecast errors and exaggerates them. Now the one last thing we want to calculate is this mean absolute percentage error. So here's what I'm going to do. All that really is the deviation in absolute value divided by the actual value times 100. So what's the 100 doing? Well, the 100 is shifting the decimal place, because this percentage that I'm calculating as the deviation divided by the a sub I should never have that being greater than 1. I wouldn't think. If it was, that'd be, I don't know how we'd get there. I guess I can't think of a circumstance when we would get there. But this mean absolute deviation, the mean absolute percentage error, so MAPE, is equal to the average of each of these percentages. Now the one thing we can do with this number is we can compare not only across models, but we can compare across data sets and see, okay, well, what is it that's giving me the smallest percentage error? How come can we do that? Because as soon as we did this division problem in here, the units on these numbers went away. So number of patients, 83 patients, the absolute value is still off by 6 patients, but when I take the ratio of patients to patients, the patients go away, and I'm left with a unit-free measure. So unit-free measures, kind of like in econ, if you recall, we had elasticity measures, make it so that we can do comparisons across different types of products, different types of processes. Okay, now, what do we do with these error calculations? Well, first off, as it sits, not much. But if I wanted to try a different forecasting method, I could maybe compare the errors to the different forecasting method to the errors from the simple forecasting method. And if I can reduce the size of my errors, then maybe I can say I have a better model. Now, our goal is not to get the errors to 0, because that would mean that out here in time, when we're actually running forecasts forward, that's a little too heavy of a restriction to think that our forecast is going to remain perfect outside the data set. So remember, we're not trying to make the deviations 0. We are trying, however, to make them relatively small. I'd like to get this bias down towards 0 as well. A bias of 0 means no bias, which is something linear regression is supposed to give us as an unbiased estimator. Anyway, hopefully this helps. I hope you see how to use Excel to calculate each of these different types of error terms. And next time we'll be moving on to a module 9, and it will give us a methodology for monitoring the errors.